You're already familiar with the equation of a second-order system? Then it's time to dive into how it behaves, particularly when it comes to the transient response. Here, we will study the percentage of overshoot, the peak time, and the settling time. Stick around because I'll be walking you through everything you need to know about transient responses, step by step. And don't forget to like or subscribe. Hello, welcome back. Today we're talking about the transient response of a second-order system. Therefore, I will go over with you about a couple of terms. So first, a couple of things. We have the rise time noted as TR, which means that we go with a system response from 0 to 100% of the final value for an underdamped system, which is in our case most of the times happening. Or from 10 to 90% of the final value if we talk about an overdamped system. The settling time, TS, is a very important parameter as well. It says that our system response settles within a 2% or 5% regime of our final value. Then there's a peak time, TP, which is the time when the first peak occurs. Fourth, we have the delay time, TD, which is that our system response reaches a half of the final value for the first time. And most importantly for all of you guys, if you ever get a control engineering position in the industry, is a percent of overshoot, noted as MP. So MP can be calculated by the system response or output's value at the peak time, TP, minus the output's value at an infinite amount of time, or final value. And this gets divided by the same variable. Usually, because it's percent of overshoot, we multiply this by 100, and that's why we get a percentage value. There are two other things which you have to keep in mind. What is really the transient response? The transient response is basically the behavior of the system from one state to another, usually when the system is at rest before it reaches its final value. It can, for instance, be caused by an input, like an abrupt change, meaning a step input or a ramp input or an impulse input. Now I want you to focus on the example with which we dealt last time, which is the second order system of the output over the input can be defined as omega n squared divided by s squared plus 2 zeta omega n s plus omega n squared. We know that the closed form solution in time domain can be noted as xt is equal to b1 minus e minus zeta omega n t multiplied by cosine omega dt plus zeta over square root 1 minus zeta squared sine omega dt. If you wonder how you derive this closed form expression, I refer you to my previous video, which is in the playlist. Now for the rise time, I told you we mostly deal with underdamped systems. So what is a closed form expression to calculate the rise time? Let me derive this for you. So I'm putting xtr, which is the rise time, in here, is equal to b1 minus e to the power minus zeta omega n tr, and plugging this value in here, cosine omega d tr plus zeta over square root 1 minus zeta squared sine omega d tr. Now we want to set this equal to 100% because that is what the rise time is defined to be, considering we start at 0 for the system response. So I'm setting this to 1 to equal to b1, which equals 100%. Now we can see the simplification of this is taking this one and this one cancel each other out, so you're ending up with cosine omega dtr plus zeta square root 1 minus zeta squared sine omega d tr equal to be 0. This can be further simplified into tangents of omega d tr equal to b minus, by getting this term over, zeta over 1 minus square root zeta squared equal to be 0. Now this can be further simplified by, for instance, bringing this whole side on the right hand side here, divide by cosine and multiply by this one and divide by this one, that gives you the minus. But I can, for instance, as well extend this term by omega n, which I denote as such, extend by omega n, which gives me in the end minus omega d sigma. And this can be recalled from the S-plane representation. Now we can conclude that the rise time is nothing else than this formula, or the omega d and sigma you can as well express in the written out way, like such. For calculating the settling time, we look at this equation. We can basically represent the cosine and sine together as a phase shift like such. Now for the settling time itself, only the exponential term is really important. So I'm going to just set this one to be 1 for now. Next, we want to see what happens if I put 1 minus e to the power zeta omega n t divided by the square root of 1 minus zeta squared equal to be 0.98. Now, what you can see here is that I can bring this one over. I have 0.02 equal to be e to the power minus zeta omega n t divided by 1 minus zeta squared. Now we assume a very underdamped system, so make this whole thing go to 1, meaning zeta is almost 0. What we can see here now, if I delete this lower part, that I can apply the ln function on that, which results in minus 3.9 approximately equal to be minus zeta omega n t. And voila, t is nothing else than approximately 4 divided by zeta omega n. And this is equal to be 4 periods. The same can be applied for the 5% rule settling time. For the 5% rule settling time, t is nothing else than 3 over zeta omega n, or 3t. Next, we talk about the peak time. For the peak time, we know that the system's output derivative has to be equal to be 0. Therefore, I'm taking the time derivative of this function and write it down here. Of course, you have to apply the product rule. First on this part, and then you can take the derivative of this part. What we can see right away, that the 1 is a constant, falls out, and we see that this one and this one are common. You can make further simplifications to derive at this equation. From here on, you can claim that either sine omega dt, in this case sine omega d, I call it peak time, so I make this t in a p now, tp now, is equal to be 0, which follows only if omega d tp is equal to be 0, pi, etc. From here, we chose not 0, we chose a pi, so the definition goes that p is equal to be pi over omega d. And this is the formula for the peak time. Next, we talk probably about the most important figure in this whole subject, which is the percentage of overshoot. For the percentage of overshoot, I told you that when the system response, as we can draw it here, is crossing basically the desired final value, this is over time, this is x, it occurs here. So I want to know how much percent of overshoot do I have. I know as well that at this instance, I'm at my peak time, Tp, meaning I can plug in to this equation just Tp and subtract the final value, in this case 100% or 1. Plugging this in leads to this chunk of the equation. Next, I can simplify this, put it in here because I plugged in for Tp pi over omega d, which results in cosine pi plus zeta over this term in the front, sine of pi. I know the cosine of pi is minus 1, and I know that the sine of pi is 0. So this term doesn't really play a role. The minus 1 and the minus from the front of here will cancel, make it a plus, and I can simplify this one to be a sigma from our S-plane representation from the last lecture, and I can set this equal as well to be omega n zeta, and down here omega n square root of 1 minus zeta squared. The omega n's are cancelling, and I'm ending up with this term. Last but not least, my percentage of overshoot is nothing else than e to the power minus zeta pi over square root of 1 minus zeta squared, what I've basically written down already on this side. Now, as I told you, most of the time we actually multiply it by 100 because it's called the percentage of overshoot. Okay, now let's code this up in MATLAB and I show you how to deal with this kind of stuff, for instance, in MATLAB. First, I'm going to clear my workspace. Then I'm deleting the command prompt and I close all plots. Then I define my variable s to be the transfer function of the variable s, meaning like such. Semicolon, okay. I define zeta to be 0.3 of my value, and I define omega n, my natural frequency, to be 1. Then I say my system is equal to be the transfer function, which can be defined as numerator is 1, it's just omega n squared basically. Well, you can basically put 1 in there, it's fine. Divided by 1, 2 multiplied by zeta, multiplied by omega n, and then omega n squared. Okay, then we apply a step to the system, which looks like such. Okay, let's see if I run this whole thing, what shows up. Takes a moment. Okay, here's our step response. Okay, I would like to create a grid on to see easier what's going on. I do that again. Run the code, and you can see that the peak time should be approximately around 3.31. Okay. However, there are faster ways of identifying, for instance, peak time, delay time, percentage of overshoot. You'd simply have to write in the command step info sys. So that gives you information of the system. I'm executing this command, and as you can see here in my command window, I'm having given the rise time. Oh, let me bring it down in such a way that you can see it. I'm basically having given the rise time, settling time is around 11 seconds. That makes sense. The overshoot is basically 31%. We're basically at the maximum at 3.31. Well, the peak time is at 2.2, 3.2, so basically right here. But the percentage of overshoot is 37% because, as I said, it's a peak value minus 1. So you can basically say 131, you can basically say 137 minus 100 gives exactly 37%. So that shows you how to code stuff up in MATLAB in a very easy way and confirm, for instance, your calculations. Thank you for listening. I hope you liked it. If you like what I'm doing, please subscribe to my channel or like my video. That keeps me motivated, and I hope you had fun today.